Hello world, it's Siraj, and I'm going to show you how to run any machine learning model locally on iOS or Android. And I've been working on this for the past few weeks as a part of my project, DoctorGPT, which is now named Dr. Dignity to avoid naming conflicts with a certain OpenAI. And in this video, I'm going to show you how to do this for any large language model and how to run it on iOS or Android. What you're seeing here is a demo of Dr. Dignity. I've just renamed it, and it's running on my device. You can see as soon as I load that model up into memory, the VRAM, the video RAM, shoots up to 2.18 gigabytes. And as soon as I ask it a question, it's going to shoot up even more. This is taking up a lot of memory, but the point is that it's running locally, which is great because offline models offer privacy for patients in this case, or anything really. They also offer freedom from OpenAI or any sort of paid API that you would have to use. And it gives you an opportunity to have complete ownership and control over your own machine. So I think this is a super useful idea of compiling machine learning models to work not just on Nvidia GPUs, but any GPUs, Qualcomm, AMD, TPUs, any type of processor, not just Nvidia GPUs. I'm going to show you exactly how I built Dr. Dignity, but in order to get there, we're going to start small and we're going to build our way up because this can be kind of complicated. So I want to start small if you're a beginner, which I hope you are. This video is aimed to be accessible to anybody. And I want to get you to the point where you understand how the Tensor Virtual Machine works. And that's the core technology that I used to get my machine learning model to run on iOS and Android. And you can see I have Android Studio up as well, not just Xcode. And I have an Android version of the app and all of that. And this is all using the Tensor Virtual Machine to work. But before we talk about the Tensor Virtual Machine and all that, we got to start small. So let's build a very simple language model in Python. And then we're going to continually build up from there. Okay? So let's talk about our dependencies. The first dependency that we're going to need is Python for programming. That one should be obvious. The next one is NumPy. Now, what NumPy does is it allows us to speed up certain operations on a CPU. And that's what we're using in this Google Colab notebook. It's using a CPU created by a company called Intel. And I'll explain what that is and what the difference between that and a GPU is later. Then we're going to use CUDA. And CUDA is NVIDIA's programming language for programming on their GPU. Now, NVIDIA isn't the only game in town. There are other GPU providers out there like Apple, and Apple has their own language for programming their GPU. It's called Metal. Now, it's not just Apple. Android has a lot of different vendors. They've got Qualcomm, Huawei, all these different MediaTek, all these different companies are creating GPUs. And Vulkan is an API that lets us use those GPUs. It's a general purpose API for all these different Android GPUs. Then there's the Tensor Virtual Machine, and that allows us to not have to worry about Metal or Vulkan, just use our language model directly from Hugging Face and compile it down to iOS and Android. But before we do that, I need to show you how it does that by introducing you to Metal and Vulkan. And we're also going to use this language called Relay. And Relay is a part of the Tensor Virtual Machine. It's an intermediary language that takes any language model, whether it's in PyTorch or scikit-learn, converts it into an intermediary language and compiles it down to a hardware-specific runtime, whether it's a GPU, a TPU, anything. And the last library we're going to use here is MLC LLM. And this is a wrapper around this Tensor Virtual Machine library, and it's how I got Dr. Dignity to work. So we can install all the dependencies that we need right here. PyCUDA for writing CUDA code inside of a Google Colab notebook. We're going to install Vulkan because we want to use Vulkan for Apple GPU acceleration later. Then we're going to install the Tensor Virtual Machine, and that was created by Apache, which we'll use at the end. And then at the very end, we're going to use MLC, which stands for Machine Learning Compilation, LLM, which stands for Large Language Model, which is a way of using the Tensor Virtual Machine specifically to compile large language models, not just any machine learning model like a time series model or regression model, but a large language model. And so that's the idea. We're going to see it download all these dependencies. And as it does that, we're going to go right to our first step. So our first step is to build a simple language model in Python. Now, this model it's going to do something very simple for us. It's going to predict the next character in a sequence based on the previous characters. And this model is trained on a data set of individual characters, just 5 of them, A, B, C, D, and E. That's it. And the way we're going to encode these vectors or encode these characters into a way that our model accepts is using a technique called one-hot encoding, where we turn any sort of categorical variable, in this case characters, into a column which represents that value as either a 1 or a 0 in a matrix. And this is a great way of representing data so that we can perform next character prediction on it with a neural network, a very simple neural network. So let's look at what this code looks like right here. I've commented it out with the help of ChatGPT, of course, extensively. So the first thing we're going to do is import NumPy. And once we have NumPy for those matrix operations, we're going to initialize our vocabulary. And our vocabulary is only 5 characters, A, B, C, D, and E. And then we're going to map all of those characters to numbers using this mapping function, this dictionary. And that is our one-hot encoding. Once we have our vocabulary, that's all the possible words that our language model could output and all the possible inputs as well. It's kind of the search space of this language model. Now, normal large language models have a search space of alphanumeric characters, not just alphabets, but also numbers sometimes. But in this case, we just have it small because we want to be really small about this, really simple. We'll initialize a weight matrix for this neural network. Now remember, neural networks operate in terms of a very simple principle. Input, whatever your input data is, times weight, a weight matrix, add a bias value, and then activate. Take all of that output and input it into an activation function, which will output a value. And then that value is then compared against the target value. And then we compute the difference, and we use the difference to compute what's called a gradient. And the gradient is using calculus pointing us in the direction of how to point the weight matrix to be more and more likely when multiplied by our input to give us the expected output. So there's the data initialization. Then there's the training loop where we train this weight matrix of our single layer neural network to continually improve that weight matrix to be more likely to predict the next character. And then we perform inference. And inference is a step where we perform a forward pass on any given input, whether it's A, B, C, or D, inside of this trained model. And it's going to give us an output. And you could see the output given A is going to be C. So it's already predicting the next character. And the way this worked is by training this model on what's called the CPU. And the CPU is a processor, and it's a part of every computer. Every computer has a CPU, and a CPU computes 4 steps in order whenever we're running it to perform any program. The first step is it's going to fetch instructions from memory, whether it's multiply, add, divide, whatever it is. The next step is to decode those instructions into commands. Those commands are specific to that CPU architecture. The third step is to execute those commands. And every CPU has an arithmetic logic unit, which contains all these possible logical computations that could occur. And the last step is once those computations have occurred, store those results in memory. So the full data flow looks like this. From RAM, which is our temporary memory, random access memory, we're going to go into the L2 memory cache, which is a temporary buffer before we get to the end. And the reason that we have an L2 and an L1 cache in a CPU is because it allows us to be more efficient in terms of temporal and spatial allocation of resources as well as processing data. It's literally spatial on a motherboard or spatially divided on a CPU where these operations are occurring. And this matters when it comes to nanoseconds and picoseconds of processing time. And so remember, it's fetch, decode, execute, and then store. Fetch, decode, execute, store. That's how a CPU works. It's pretty simple stuff. And we can actually clock how fast this works on a CPU with this inference function, which you can see here. So this inference took 0.07 milliseconds. Once our trained model was trained, our language model, giving it an input, it took 0.07 milliseconds to run that model and to predict the next character. That's kind of cool, right? 0.07 milliseconds. Now, you can imagine a lot of these larger language models like Dr. Dignity, they're not going to take 0.07 milliseconds. They're going to take 20 milliseconds or 30 or 50 or 1,000, right? If you have a 70 billion parameter model. So we really want to make this fast. Maybe not for this model, but at scale, it matters. So how do we do that? How do we surpass the performance of a CPU? Well, we have to introduce another processor entirely because we are limited by the capacity of the flops, the computing capacity of the floating point operations per second of a CPU. That's why we have to introduce another processor called the graphics processing unit, or the GPU. And the GPU has more cores, way more cores than a CPU. And it allows us to be able to access those cores in a very specific way. Now, the GPU is good for a lot of things, but it's not good for everything. The CPU is great for sequential operations. The GPU is great for parallel operations. Now, when would we want to use parallel operations? Well, in the case of neural networks, like in the case of inference. So when we are running inference on tokens, let's say we give our large language model a sentence and we want it to answer that sentence. Well, we could give it one character at a time, but ideally we could give it all the characters at the same time and it would be able to process all of them so that it could give us an output faster. Well, the way to do that is to create a bunch of threads, and each of these threads are operating in parallel. And these threads live in what are called blocks, and these blocks live in what are called grids. And there's a great way of understanding how this works. Oregon State has this great slide deck that I found here on how CUDA works and how that pipeline works. But the idea is that we can have some code, and this code could be in C, and it could just be iterating through a loop. That's all this code is doing. But if we want it to run on CUDA, then it changes just a little bit by introducing these variables like block ID and thread ID and grid. Well, what are grids, threads, and blocks? This is a way of subdividing data and processing it in parallel for the GPU. And this is NVIDIA's paradigm for GPU programming. We have a grid. And a grid has a bunch of blocks, and a block has a bunch of threads. And we can very carefully run different computations in parallel and sometimes sequentially and have these threads and blocks share data with each other. And you can imagine a wide variety of applications that we could use this for. And what it was originally used for was graphics processing in games and videos. It's called video RAM after all. But actually it's great for deep learning, because deep learning matrix operations require tons of parallel computations, multiplications, additions, all this stuff. And so we want to be able to do that. And specifically, we could do a lot on the GPU. We could run training on the GPU. We could initialize our data loader on the GPU. We could do a lot on a GPU. We could run inference in parallel. And this is called data parallelism, when we have data that is being fed into the model in parallel. And you can see that NVIDIA has all of these docs for CUDA. It has been around for over a decade. It is clearly the most supported, most popular GPU library out there. And thank you, NVIDIA, for creating it. Your stock price reflects that. But NVIDIA is not the only one on the block. Okay, but I want us to know how CUDA works. That's why I'm explaining it to you. And we don't want everything to run on CUDA. We only want that part to run on CUDA that we need to be parallelized, because we have a program and it's written in C, C++, Python, whatever. And it has some portion of it in CUDA. And then we have a host code, which runs on the CPU. And then we have CUDA code. And the CUDA code will compile it. Remember, CUDA is not just a compiler, it's also a runtime. So it compiles code and then it runs it as well. So that code is compiled, it sends it back to the CPU. If it needs more GPU processing, you send it back to the GPU. And then if it's processes there, then it stores the result back on the CPU. So you can see how this process works. And we can initialize and run our own CUDA operation inside of a Colab notebook by installing PyCUDA. And you can see it right here. And once we run PyCUDA, you can see us running the inference function in CUDA as a specific kernel where we have threads, blocks, and we are going into this thread and block, and we are performing all those operations in parallel. So that is going to give us a speed up. So when we run this measure function to measure the inference speed on an Nvidia GPU, and we need to connect to a T4 GPU here to do that, I'll connect to one, then we can see that the inference speed is even faster, which is awesome. That's what we wanted to see. So the inference speed is faster. That's awesome. But like I said, Nvidia is not the only kid on the block. There's a lot of other kids on the block, like Apple. And unfortunately, Nvidia doesn't have GPUs on iOS or on Android devices. So we need to find alternatives. So how do we do this? Well, Apple has its own GPU. It's called the M1, the M2 for the MacBooks, but it's also got the A1, the A series for the chips, A15, A16 Bionic chips. And the way to program the GPU on these chips is to use Apple's native API called Metal. And Metal is an amazing technology. And what Metal lets us do is, it's just like CUDA, both a compiler and a runtime. It lets us take a high-level framework like PyTorch, a model written in PyTorch, and it lets us run some of those functions on the A15 chip or whatever chip our iPhone is on. And so let me show you how to do this. We're going to convert that code into Metal code. And unfortunately, we can't do this in a Colab notebook because it's using an Nvidia GPU on a Colab notebook. So we'll open up Xcode. And let me show you in Xcode what this looks like. So in Xcode, I have this file here, and this is essentially an Objective-C implementation of our language model. It looks the exact same, and I can run it right here. I'm going to hit run, and it's going to build, and you can see the output of the build right here. Boom, it just built. Okay, and you can see that it's actually being programmed. Inference took and you can see I'm actually timing it in nanoseconds because it's that fast. Milliseconds just showed up as 0 whenever I clocked it in milliseconds. So I had to redo it in nanoseconds for it to show up and register. And so here's the Metal function, right? So we create a .metal file. We paste in this inference function in .metal. Now remember, this is it, this Metal std library. It's just an Objective-C library, and we can just input it right here. The rest of the code is just in Objective-C. And that's it. It's Objective-C code for a large language model. We load up our Metal program, the GPU buffers, the memory, and we do our computation on one end and we do our allocation separately, just like a good GPU programmer should do on CUDA. It's very similar. And that's it. And that's how we run a small language model on Metal devices on iOS. But let's keep going, right? So that's the Metal devices. Let's do it for Android now, okay? So Android also is the biggest mobile operating system in the world, like by far, right? So 71% market share as of last year. Sorry, Apple. And Android has a lot of different GPU vendors: Samsung, Samsung, Qualcomm, MediaTek, Unisoc, all these different ones. And OpenGL used to be the library of choice for graphics processing, but it was deprecated and really bad and old. So Vulkan is now the successor to OpenGL, and it uses much less CPU than OpenGL. It's much more heavily reliant on the GPU. And while OpenGL required the specific companies to update their drivers for their GPUs, Vulkan puts that responsibility on the developer. And what that allows us as developers to do is, even though our code is going to be so much more verbose and difficult, it's going to allow us to create one API that runs on any GPU. And that's huge. 70+% of mobile devices run Android. So as hard as Vulkan is, if we learn Vulkan, one language can run on 70% of GPUs that are non-NVIDIA. That's a huge deal. So that's how Vulkan works. And you can see that Vulkan really, it wasn't just meant for Android. You can even run Vulkan code on NVIDIA GPUs or Apple Metal. So it's almost like a general purpose GPU programming language. And that's why it's called video memory, right? It used to be used for all of these graphics processing tasks like rasterization and vertex assembly and shading and all this rendering and ray tracing and all this stuff. But now we're using it for matrix operations for deep neural networks, specifically large language models. And so we can see the Vulkan code right here. And it took me quite a while to output all this Vulkan code. I had to ask ChatGPT to output this code in small bits to fit into its context window. That's how big this code is, this Vulkan code. You can see me asking ChatGPT over and over and over again. I'm going to paste all my ChatGPT prompts for you in the video description. But you can see here what this code looks like for Vulkan. And I paste it into Visual Studio Code here. But it's all written in C, and Vulkan is a single header right here. But we create a Vulkan instance. We say, here's our physical device. Here's our simulated device. Here's what our pipeline looks like. Here's our command pool. What commands are we going to use? Here's the buffer in memory. And then here's the pipeline of compute. It's a lot of stuff. And I'm telling you, this is quite a lot of code, but I'm sharing it with you in the description. It's 338 lines of code, but it compiles and works. And I can show it to you right here. I'm compiling it, boom, and it works. And so I've got it running right here, Vulkan 2, awesome. And you can see the binary right here at .vulkan 2. But the idea here is that instead of using, I had to repurpose this idea of a shader. And shaders are from graphics processing, right? They're a way to create, all sorts of effects, but we can use shaders for tensor operations as well. In this case, just running a simple computation from inference on the device. In this case, Vulkan running on my MacBook, which would be the M1 chip, but Vulkan can run on Android as well. And so let's move on to the next and final step here, which is the Tensor Virtual Machine and why this matters to you. So we could learn Vulkan. It's very verbose. We could learn a Metal. It's also very verbose. And there's tons of different GPUs out there, right? Those are not just the only two. Each GPU processes data differently, and there's many different techniques that we could use to make inference faster on a GPU, right? We could use something like data tiling, where we, share data as it's being processed in a way that is more memory efficient across GPUs. We could use memory coalescing and loop unrolling and vectorization and all this stuff, batching and pipeline parallelism. And that's general purpose. There's also specific optimizations that apply for specific types of GPU vendors, like shared memory in CUDA or warp shuffle. But in Metal, there's thread group memory or performance shaders. But in AMD ROC, there's local data shaders and wavefront optimizations. And in OpenCL, you see where I'm getting to? This is hard to learn. There's a lot out there. And so what we want to do is we want to learn one tool that will compile down to all this stuff. And it will let us take our simple Hugging Face model and run it on our Android device and our iOS device or every device. And that technology is the Tensor Virtual Machine. And that's what brings me to this. So let me explain to you how the Tensor Virtual Machine works. This thing is awesome. It was created by Apache, a company that's well known in open source software for a bunch of different technologies already. And the way it works is we take our machine learning model, whatever language it's in or framework, whether it's in PyTorch, TensorFlow, Keras, MXNet, whatever it's in, and it compiles it into this language agnostic language called Relay. And what Relay is it's a way of defining the computation graph of our machine learning model. And from that intermediary language, this optimizer is applied. And what that optimizer does, it's called the auto TVM optimizer or auto scheduler. What that optimizer does is it breaks that computation graph down into subgraphs. And each of those subgraphs is then optimized for individual hardware that we're targeting. And it's going to guess and check a bunch of different subgraphs and see which ordering of addition, multiplication, activation functions, all this stuff, which ordering of these operations is the fastest for a given target hardware. And at the end of this process, by the way, it's a gradient-based optimization process. It's essentially a decision tree, an XGBoost decision tree that's optimizing, finding the optimal subgraph. Once this process is complete, then it quantizes that model to be as small as possible. And quantization is the process in which all the weights and activations of a model are made smaller, so they're less precise, but they take up less space, and it's faster for inference. And so that's the idea of the Tensor Virtual Machine. And the TVM, the Tensor Virtual Machine, I'll call it the TVM from now on, is both a compiler and a runtime. Just like CUDA, just like every other Metal, all of them, they compile it down to a language and then it runs it as well. And so, like I said, that graph is created from whatever framework we're using, and that graph is then optimized. And not only is it optimized, it's partitioned. And that means it's chunked or sharded into little bits, little, in the case of PyTorch, .bin files. And these .bin files, you can see, are a way of, having the model load up a large language model into memory. Even though it doesn't have that much VRAM, it could load up a part of a .bin file. And that lets smaller GPUs run these models, right? If it's sharded as opposed to one giant bin file. Only an Nvidia GPU could probably run something like that, a big one. And so that's the idea. And so it's performing this kind of code generation, right? Because it's, on one hand, it's optimizing this graph using all these different subgraphs. On the other hand, it's generating code for the different hardware that it's being targeted for, whether it's CUDA code or it's Metal code, Vulkan code. It's kind of on top of all of these technologies. So we can just take our PyTorch model, give it to the TVM, and then build it into Relay, this intermediary language, and then from Relay, compile it down to iOS, or compile it down to Android, or Nvidia, or whatever we want it. Okay, so that's the idea. And in here, you can see a little bit more detail around how this subgraph optimization is happening. And this is really important because there's this idea of both abstraction and transformation. And if you're interested in this technology, by the way, you should definitely read up on. By the way, this is Apache's Tensor Virtual Machine. You can see this overview that they have of all of it and how it works. It's super, super interesting. But there's this course called Machine Learning Compilation Course, MLC.ai. Go check it out. It explains how automatic program optimization works, how the Tensor Virtual Machine creates all of these different transformations, stochastic transformations, to take an original program and create a bunch of possible programs and then select the best program, the most optimal program for your specific hardware environment. So definitely check out MLC.ai, the course, as well. And so this idea of abstraction is super powerful because once we abstract a computation graph from any sort of vendor lock-in, then we can perform a bunch of transformations on it. So there's two ideas, abstraction and transformation. And you can see that different transformations of these matrix operations can yield different results. We can cache things. And remember, I talked about earlier, we could do all these fancy techniques like data tiling and vectorization and loop unrolling and all this stuff, right? So this can be super complicated. And so there's this idea of, in this intermediary language called Relay, which the Tensor Virtual Machine uses, you can see that it's going to generate code for a specific target, whatever target that is. And we can specify what that target is going to be. And there's a bunch of operations that could be applied. You could fuse different operations like multiply and add together to take up less space. It could parallelize them. It could vectorize them, all these different things. And so there's a 6-step process here, right? The first step is we import our PyTorch model. The second step is we optimize this model. The third step is we partition this model into small chunks. The fourth step is we generate actual code to run inference for iOS and Android. The fifth step is we package it for iOS and Android. And the sixth step is we deploy it and we start running it in Xcode and Android Studio. Okay, so that's the 6-step process. Let's go through this code right here in Python. So first we'll import the Tensor Virtual Machine as well as this language Relay. And once we have that, then we're going to load up this PyTorch model. This PyTorch model is just called Fashion MNIST. It's a super simple image classification model just for training purposes. I just wanted to show you how we can take any PyTorch model and convert it to both Android and iOS, even though before we just built this small language model from scratch. In this case, we're going to use PyTorch. So I just want to specify that in case you got a little confused, okay? And so there's only 9 different class names here: pullover, trouser, sneaker, sandal. And we can just download this pre-trained model and then run inference on this pre-trained model. Now this model has several parts, right? It's got a model structure, a skeleton to the model, the computation graph, and it's also got weights and it's got parameters. And now we can take this model and we can optimize it for Android and iOS. We can compile it for Android and iOS using the Tensor Virtual Machine. I've been trying out a bunch of different models for Dr. Dignity, and we can see in my GitHub project that I have gained a lot of attention around Dr. Dignity. It's super interesting, but I want to say that the 7 billion parameter model was way too big to be running And I get that now. Like it's too big to be running on most mobile devices. 3 billion parameters is the sweet spot. Unfortunately, we can't do more than that. We can only move forward. We can't move backward. And so when it comes to 3 billion parameter models, there's quite a lot of them. And this open LLM leaderboard is constantly being updated on Hugging Face. So I recommend you check it out. But what I like to do is I like to look for actual 3 billion parameter models, not 70 billion parameter models. And I want to see how they're doing here. And you can see that there's several models that are at the top of this list. And one in particular that really got to the top of the Open LLM leaderboard is Mark's 3B v2. And Mark's 3B v2 is Open Llama 3B v2, which was an open version of Meta's Llama v1, but a 3 billion parameter version trained on GPT-4 conversation data. And this is a similarity with a lot of the Open LLM leaderboard. Like a lot of the top LLMs were fine-tuned on GPT-4 data. And this kind of heralds this other paper called Your LLM is Secretly Your Reward Function, is what this paper was called. And this idea is that we can just use a teacher language model to train a much smaller language model rather than fine tuning. And the idea is that it's going to improve accuracy by a lot because it's a much better representation of the data, and I should say knowledge, not even data, of the knowledge. And so there's a lot of ways of quantizing this model and whatever, but Mark's 3B was the best for 2 epochs. It was trained with more epochs. I'm sure it could be improved. There's a lot to be improved here. But you know, I couldn't get any of these models to compile down to Android or iOS using MLC LLM, except for RWKV Raven. And this model is a recurrent network that offers transformer level performance. Super interesting stuff. Reinventing RNNs for the transformer era. This idea of attention is all you need took the world by storm. But the idea is that we do still need recurrence. Recurrence didn't go away. Recurrence actually gives us optimization and speed at inference, right, over transformers. So this offers transformer level performance during training, but recurrent network level performance during inference. And this kind of mixes both ideas of attention and recurrence together. It's called receptive weighted key value, and I recommend you check this paper out. It's super interesting, but the idea is that this is super light and it could work, and this is what I used. And so let's look at how I was able to use that. So if we go to the MLC MLC LLM documentation, and let's go through this list together. The first thing we're going to do is we're going to install MLC LLM. Now, MLC LLM was created by a few researchers, and the idea is that they are trying to make TVM Unity much more accessible to people who want to run large language models on their mobile device specifically. And they have this app called MLC Chat, which I basically white labeled for Dr. Dignity. And I had to, rebuild it and do a lot of different things to make it unique enough to get on the App Store. But it is on the App Store, by the way. My app is now on the App Store. You can see it right here. It's still a work in progress. Don't expect anything too, amazing or fancy or anything. I just barely got it on the App Store. There's still a lot of work to do, but it's there. So you can download it for iOS, and I'm working on Android actively right now, okay? So please be patient with that. But this idea of MLC Chat, machine learning compilation chat, it shows you how you can use their GitHub repository. So let's do that together. If we go to this MLC Chat, if we want to compile a model with MLC, we'll first git clone their repository. And once we git clone the repository, then we're going to cd into that directory and install all the pip dependencies that this library has. And there's quite a lot of them. But once we do that, then we can build, we can compile, I should say, any model we want directly from Hugging Face to Android or iOS. And I want to show you exactly how we're going to do that. Then we'll cd into that directory, and then we'll run sudo pip install to install all of the dependencies one by one. And once that's done, we can verify our installation by running python mlc llm.build and / help. And that'll let us know if it was installed. And it looks like it was installed. Now we're going to click on Android. And what we want to do is we want to build Red Pajama 3 billion v1 for target Android. Max sequence length is 768. How many output tokens? And quantization, Q4F16. So this is just a format for how much do we want our weights and our activation functions. What format do we want them? Do we want them in bits, 16-bit versus 4-bit, right? That's it. It's a standard format. Now, we don't want to do this for Red Pajama. We want to do this for RWKVV. And now it's going to do that subgraph optimization process I talked about. And it should look something like this, where we're going to go up and it's going to build all of these things. And basically what it's doing is essentially what I told you. It is taking that giant PyTorch file, and then it is abstracting it into the relay, this intermediary language. It's applying a bunch of transformations to it. And this is, using XGBoost, where we're taking that computation graph, we're subdividing it into subgraphs. We're trying out a bunch of different ones for our target device, in this case, iPhone. We're executing the functions and seeing how fast they run. And we're using that to create an optimized final output graph. And that graph is saved. And once we've saved it, we can ls and see that, do we have it? Yep, we have it. And we can see, do we have the parameters as well? Yes, we do. We have those as well. So we've got the parameters, we have the tokenizer, great stuff. So now that we have that, now we can build our app from scratch. So how do we do that? The first thing we do is we clone the iOS app, or we clone MLC LLM. And now that we have MLC LLM, we're going to make a distribution directory. We're going to clone all the pre-built libraries into that directory. And we're going to clone the model into that directory as well. Then we're going to build the auxiliary components by going to cd iOS. And then by preparing libs.sh, we're going to prepare those libraries to run for iPhone. So we'll run prepare libs.sh. And this is using Rust, by the way. The Tensor Virtual Machine is using Rust. It's building it perfect. It built this runtime for iOS. And you can see I have all these library files for iPhone, and I can prepare the parameters as well. I'll run that. Perfect. And now I can build the iOS app. So I'm going to open the app in Xcode and then build it. And what you're seeing is the final version of this, but it's got RWKVV. You can see all the .bin files. You can see my MLC chat config where I say, this is my model file. Here's my local file. Here's my template. You need to have this stuff working for MLC chat to recognize it. Here's the app config. I've just got RWKV Raven. In the linker, another thing you need to do is build phases. We need to go to link binary with libraries. MLC Swift should be here. We should go to build settings, and under other linker flags, it should have these under them to link all the modules, and then we can run it. And you can see it's running. And it's taking up a lot of memory, but hey, it's running locally, which is awesome. So that's the idea behind iOS. And now let me show you Android. So if we go to Android, they've got a pre-built Android package as well, but we're not going to use that. We're going to do this same thing, but for Android. And I will say that I'm still having some trouble running my Android MLC LLM. I've got it open in Android Studio here, and you could see that I've built it. We basically do the same thing for the Android version, where we build the model for the target, which is Android, in this case, Vulkan. It's going to output Vulkan. And then in our appconfig.json, we specify that model. We specify our Android NDK path, our TVM NDK path, our Java home path, and our cargo path. And cargo is Rust. It's Rust's package manager, just like Python has pip. And I just want you to know that. We need to set the right Java version. I'm still working on that. But that's where we are so far with Android. And, that's the idea, compiling it for Android. Check out MLC LLM. And what are the future directions here? I want to take a bit to kind of reveal my future directions with this project. Now, I am a YouTuber and I make videos, but this idea, this app, Dr. Dignity, it really is meaningful to me. My parents always wanted me to be a doctor growing up, and they never kind of let me be myself. They were always like, you need to be a doctor. And I might not be a doctor, mom and dad, but I will make Dr. Dignity happen. And I want the world to know that as well. I'm going to continually improve Dr. Dignity. It is still an open source project. That means you can white label my app and make it your own for whatever use case. But who knows where this project is going to go? I really do believe in the vision of a doctor in everyone's pocket for free. And I want it to work, and I want it to work really well, and I want it to save lives, and I want it to be better than a human doctor, because human doctors misdiagnose all the time. And so how do we do that? Well, right now I've got RWKV 3 billion running, and I got to port it to an Android APK. Then I want to fine tune Mark's 3 billion on even more medical data to pass the medical licensing exam, and do the same for Android. Then I want to add code to it by fine tuning it on code, and use that as a code interpreter. And the code interpreter is going to create SQL and Python commands on a local database on medical research papers that I have saved locally to cite its sources whenever it gives you a response, which is what we want a medical LLM to do for us. And then we want to continue training it on all modalities of biomedical data, not just text, but images, video, tabular data, everything. And then we want to port that over to iOS and Android. And the last step is to add a nice video avatar interface to this so that we really give Dr. Dignity an identity. And we want this all running locally, HIPAA compliant. Patient confidentiality is preserved on a user's Android or iOS device, no OpenAI necessary. And the way to do this is to use a Tensor Virtual Machine. And so if you're interested in this project, please check out DoctorGPT. It's also called Dr. Dignity now on GitHub. Subscribe to me on YouTube. Make a contribution to this project. That would be the most useful thing. And until next time, happy compiling.